What is a logarithm? Let's graph the exponential function to find out. Given the graph f of x equals b to the power of x, b is greater than 1, so we know that we have exponential growth. Let's graph it and also graph its inverse. So when it comes to b of x, or b to the x power, if we build an xy table, we can just imagine we plug some points in, like for example, let's plug in -1. If we plug in -1, we get b to the -1, or that's the same thing as 1 over b. If we plug in, let's say 0, anything to the 0 power always gives us 1. That's a nice easy point to plot. And also if we plug in 1, we will get the value of b. Okay, so if we graph those at -1, here's -1, we'll get the value of 1 over b, pretty small. Here's 1. If we plug in 0, we'll actually get 1. And if we plug in 1, we'll get some value b. Let's call that b up here. Okay, so this is going to be the point 1b. Here's our point -1, 1 over b. And then over here is our point 0, 1. You can see here our graph is an exponential growth graph, just like that. Okay. All right, let's go on and graph its inverse. So its inverse will be in green. Now, one thing we know about inverse functions is that the x and y values are always switched. So for the inverse, what used to be -1, 1b, 1 over b, is now 1 over b, -1. What used to be 0, 1 is now the point 1, 0. And what used to be the point 1b is now the point b1. Let's graph those points. So here's 1. Let's go ahead and plug in 1, 0. We also have the point b1, so b is going to be way out here. We'll be at b1. And then we also have the point 1 over b, -1, so that'll be somewhere here. Okay? And you can see that this graph is actually going to go this way, down, and then now we're actually not going to touch the y-axis, just like the other one didn't touch the x-axis. And then we also see that because they are inverses, we have a reflection across the line y equals x. And we see that reflection occurs there. Notice how all those ordered pairs are also matching up. Okay, so we have the point 1, 0. Notice that's a switch of 0, 1. Here we have b1, and here we have 1 over b, -1. All right, well, the green line is actually what we call its inverse, which is a logarithm. Okay, and so the way that we write logarithms typically is on the calculator, you might actually end up seeing it as a log base 10. The way we write log base 10 is typically just log, like that. Okay? If you do not have a base 10, then you might have like a log with a base of 3 or a base of 2, whatever that might be. But if you have a log base 10, you actually don't see a number as a little subscript there. It's left blank intentionally. Okay? Some other examples of logs are if you have a very special log where it's log base e of x, then we would actually call that the natural log of x, ln of x. Now, one technique to converting logarithms into exponentials is what I would call the loop trick. Okay, so if I have an example of, let's say, log base 3 of x equals y, then what we can say is using the loop trick, converting that into an exponential, we can say 3 to the power of y equals x. That's how you can rewrite it as an exponential. Okay? Similarly, if we had log base e of x equals y, then what we're now saying is e to the y equals x, like that. Okay? All right, so some real-life examples of logarithms. What are some real-life examples of logarithms? Well, here in the Bay Area, one thing that we're very familiar with is earthquakes, and we measure earthquakes using something called the Richter scale. And the Richter scale is using the power of logarithms to determine how strong an earthquake is. Okay, so because logarithms are typically in base 10, what it's telling us that is that on the Richter scale, let's say an earthquake of magnitude 3.0 versus a magnitude of 4.0, it may not seem like a lot, but it's actually 10 times as strong, 10 times stronger. So that's something to be aware of, that just because you go from 3 to 4 and then 4 to 5, it doesn't mean, oh, it's just like a little bit bigger. It's actually 10 times as big as the previous case, okay? And 10 times as big as the other case. So really you're talking 100 times bigger as you get into a Richter of 5.0, okay? All right, some other things that use logarithms. You can also use logarithms in other applications like finding the decibel level, so the loudness of sound. And you may have even seen it in chemistry when you look at the pH scale. The pH scale also uses logs. Okay, so those are just a few examples of the ways you can use logarithms in applications. All right, so a logarithm is just a power. As we said earlier, if you have log base 2 of 32, that's the same thing as 5, because if we do our loop trick, it's like saying 2 to the 5th is equal to 32. See that? So the logarithm with base 2 of 32 is 5. Okay, so let's take a look here. The logarithmic function with base a, where a is greater than 0, remember that a always has to actually be greater than 0, and a can also not equal 1, is denoted by log base a of x. Now, why is this the case? Well, take a look at what we're dealing with here. Remember that when it comes to the exponential, that b value always had to be greater than 0, if you recall, right? We always had that have that b value greater than 0. It can either be between 0 and 1, or a value greater than 1. So the same thing works for logs, that the logs have to be basically a value greater than 0. Okay? All right, so we defined our function, as we said earlier, using the loop trick as a to the y is equal to x. Using the loop trick, we can rewrite it like that. A to the y equals x. The domain of the logarithmic function, as you see in our graph up here, you see that it goes from the y-axis and it only goes forward to the right. So we see here, that the domain of our function is all values from 0 non-inclusive, because there's an asymptote there, to infinity.